So we've been talking about chemistry. We've been talking about atoms and atomic numbers. And I told you that one of the important things about atoms is the number of electrons and the number of vacancies in the outer electron shell. And all of that was to get to this discussion, the different kinds of bonds in biological molecules. So there are three different kinds of bonds that are particularly important in biology. What do we mean by bonds? Individual atoms might be this hydrogen or this oxygen. When they are held together to each other, they are held together by what is known as a bond, right? They're glued together. Now, there are three kinds of biological bonds that are important: the hydrogen bond, the ionic bond, and the covalent bond. So hydrogen, ionic, covalent, these are listed in the order of weakest bonds to strongest bonds. Now, you might wonder, why do molecules need more than one way of getting stuck together? Okay, I don't know why molecules in general do, but for biomolecules, the reason they've got three different kinds of bonds is the same as the reason that our clothing gets put together by different kinds of bonds. For example, you are probably wearing pants. I don't know, we're all in the quarantine, maybe you're not, but probably wearing pants. And if you're wearing pants, like let's just say jeans, then you know that the pieces of fabric, and the pieces of fabric would be analogous to individual atoms. The pieces of fabric are put together at the seams in a way that's really strong, that's not designed to come apart at all. That is analogous to covalent bonds. Wherever two atoms are stuck together by a covalent bond, that is a strong bond. That is a place where the molecule has been put together and we don't expect it to come apart. On any given day that I'm wearing pants, I do not expect the seams to come undone. I'm relying on them. That's like a covalent bond. Now, on the other hand, even though I'm wearing jeans, I did not get sewn into my jeans today, right? I have got an area of my jeans where it's easy for me to get in and to get back out, right? That is analogous to ionic bonds. Now, ionic bonds will put two atoms or two molecules together, and they'll stay together pretty good. It's a pretty strong bond, but not as strong as a covalent bond. That is like the seams of my pants are like covalent bonds, and the ionic bonds might be like an area with lots of buttons, right? Wherever my button fly is, that is like putting lots of ionic bonds, and it's pretty reliable. My buttons don't come undone particularly easily, but in order to get into my jeans in the morning, then it's easy to get in and out of my jeans because of the movement that's allowed by ionic bonds. And then we've got hydrogen bonds. Now, hydrogen bonds are super weak. However, this is an easy thing to get confused by. This is a water molecule. A water molecule is put together by a covalent bond between the oxygen and this hydrogen and the oxygen in that hydrogen. So a water molecule itself is put together by a special type of covalent bond. However, in a glass of water, the hydrogen end of each water molecule is very weakly attracted to the oxygen end of an adjacent water molecule by this dotted line here, which is a hydrogen bond. Now, hydrogen bonds are super, 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 super weak. They're so weak that you would imagine, okay, why do we even bother with them? And the reason that hydrogen bonds, even though they're weak, they're very important, is because in water and in living systems based on water, there are just so many hydrogen bonds that even though each individual one is very weak, altogether, they can create a very strong bond. Let me give you another analogy. I don't know if you've ever looked at Velcro before, but if you look at Velcro real closely, you'll see that one side of Velcro has got little tiny loops of fabric, loops of thread, okay? That's the fuzzy side of Velcro. And the other side of Velcro feels kind of scratchier because the other side of Velcro has got like little hooks on the other side. Now, if you took one of those little hooks and hooked it to one of those little threads, and you're like, could you pull it apart? Super easy, right? Well, that is like one hydrogen bond. One hydrogen bond, super weak. But Velcro, if you put two pieces of Velcro together, you can't pull it apart. You have to peel it apart. And the reason is that when you've got Velcro put together like this, even though each individual little hydrogen bond is very weak, there are so many of them that if you try to just pull them apart, you can't. You have to peel them apart and kind of break them just a few at a time, right? So the three different kinds of bonds. Now, what does that have to do with electrons and electron shells? This is a slide from a previous lecture. Okay, it's earlier in the pack of the PowerPoint. Electrons do not orbit the nucleus randomly. They're combined to specific orbits called electron shells. And this is where I asked you to memorize that how to calculate how many electrons were in the outer electron shell and how many vacancies there were. Now, what I didn't tell you at the time is that every individual atom behaves as if it would like to have a full outer electron shell. That's the way it behaves. Every individual atom seems to be behaving as if it's going, oh, I really wish I could have a full outer electron shell. What could I do to do that? And then what an atom does in order to get a full outer electron shell is dictated, is going to dictate what kind of bonds it will make. So let's look here at nitrogen. Nitrogen is like, ooh, if I could just get 3 more electrons in my outer electron shell, I would be very, very happy, right? So there are different strategies that atoms use in order to fill up their outer electron shell. Let's start by talking about the strongest of the chemical bonds, the covalent bonds. Covalent bonds are formed when atoms share electrons. Not just sharing electrons, a covalent bond is the sharing of a pair of electrons. So let's say I'm one atom, you're one atom, and I say, I'd really like an extra electron for my outer electron shell. I am willing to share my electron with you if you share your electron with me, okay? So we will share this pair. You bring an electron to the table, I bring an electron to the table, and together we will form a covalent bond. Here's the covalent bond between 2 hydrogen atoms. Every hydrogen has got a single electron in its outer electron shell and 1 vacancy. So the 2 of them are looking at each other and says, I would really like another electron in my outer electron shell. It looks like you would too. How about if I share my electron with you, you share your electron with me, and together we kind of have full outer electron shells. Now, do they really have full outer electron shells? Not exactly, but better than they were. It's kind of like if you wanted to buy a BMW and your roommate wanted to buy a BMW, but neither one of you could afford a BMW, but together, you went together, now you've got a BMW. You're still going to tell your friends you've got a BMW, even though you're really kind of sharing it, right? That's what a covalent bond is like, sharing of a pair of electrons. We're going to talk about the different kinds of covalent bonds. Covalent bonds may be polar or they can be non-polar. You need to know the difference, okay? When 2 atoms are sharing that pair of electrons nice and even Steven, then it is a non-polar covalent bond. But there are times when instead of 2 even Steven kind of let's share this real evenly, one of those atoms is cheating. And when one of the atoms is cheating and keeping that pair of electrons for more than half the time, that creates a polar covalent bond. Okay, so how to remember that? I will share with you the way a student has shared with me that in polar covalent bonds, one of the atoms in it is a puller, meaning it keeps the electrons more than it should. Okay, so polar bonds are pullers. I make that go away. Alrighty, we are going to start here at the beginning of the next video.